Welcome to another episode of Earth is Our Home with Dr. Tom Blaine. He's going to be talking about how the climate engine works. So stay tuned. Welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with The Ohio State University, in which he talks about a variety of different issues when it comes to global warming and climate change. And today, he's going to give us an overview and a better understanding of how the climate engine works. Tom, it is always a pleasure. And I've been looking forward to this episode because you're going to be explaining some things that I really have not fully understood.
Well, thanks for having me, Patrick. It's certainly a pleasure to be here. You know, we've gone over some of things of Earth's temperature history, really. We've talked about climate history, but we've talked about Earth's temperature history, how we've had warm spells and cool spells and what's brought those on and what's caused temperatures to change over the long run and also over the short run. And I believe it's important now to get people to understand how the climate system, or as you put it also, the climate engine works. It is like an engine. It's powered by the sun. We have incoming energy from the sun, and then the rest is stuff that takes place in our atmosphere that yields terms and things that we've all heard of, but many people can't really define, even though they've heard of them. Things like the jet stream, the trade winds, and all those things. And today we're going to start getting into what those things are, why they exist. And then next time on this, we will get into a little bit about how those things are changing in response to some of the things that are happening in the atmosphere now. The series, of course, is Earth is Our Home. And that's my overall series. Thanks to you and Sarah Swanson for having me do this. It's really great to be able to share this. Right now, this is our fourth episode on Earth's climate. Today's talk, again, is how the climate engine works. So we're going to discuss that. And basically what we have to talk about with the climate engine is global atmospheric circulation. How winds and air move around the planet. Basically, this involves cells of circulation. So think in terms of cells of circulation, because we're going to do a lot about cells. This is going to lead us into an understanding of the jet stream. You turn on the weather almost any time you watch the weather, whether it's the Weather Channel or your local news, they talk about the jet stream, but very few people can define what the jet stream is. Very few people outside of weather professionals can talk about it or why it's there, what causes it to do what it does, the trade winds, high and low pressure system, the prevailing westerlies that bring us our weather here in Ohio. And that's probably where we'll wind up today. And then we're going to go back. We had already talked about what El Nino and La Nina are. And they are things that crop up due to some special ways in which the continents are arrayed now. We had talked in episode 1 about how the positions of continents dictate global climate over millions of years. Well, because of the vastness of the Pacific Ocean, in other words, the way the continents are arrayed right now, we get these phenomena, El Nino and La Nina. And it's better to understand those. I've already explained those before, but right now I want to retreat, explain the climate engine, and then reintroduce those next time in the light of an understanding of this, because this has enormous implications. A lot of people are pointing out that, hey, do we really have global warming? Temperatures in Antarctica haven't changed that much. Temperatures at the South Pole haven't changed. Why is it not warming at the South Pole? Whereas the North Polar region has the temperatures have risen quite a bit. again, we're going to need to understand Earth's circulation to understand this uneven warming that we are seeing. And so that's why I want to get into this. So look here what we've got. Meteorology 101. If you stop and think about it, the reason we have weather on Earth, the reason that we have weather phenomena is because the Earth heating and cooling from the sun is not even. It's not even. The main place that gets the most direct sunlight is the equator, right? Equator, sun stands pretty high up in the sky, directly overhead twice a year, March and September, those equinoxes. It never stands overhead here in Ohio. We never get that much radiation from the sun, that much energy, that much heat. But the equator gets a lot. So at the equator, what happens when you get all this warmth? You get rising air. Warm air rises. I think most of us have learned that in basic science or physics. If you got a package of warm air and a package of cool air together, the warm air is lighter, and so it will rise. So at the equator, you get rising air. And check that out. So this is a cross section now. We're looking at a cross section of the Earth. All right, way over on the right is 30 degrees north latitude. That would be in the continental United States. On the left would be 30 degrees south latitude. But in the middle, at the equator, we've got rising air. Now, once this air gets to the upper portion of the troposphere, it can't go into space. Physics, we don't have time to get into that, but air cannot escape the atmosphere and go off into outer space. It's stopped there by what's called the tropopause, the end of the lower troposphere. Well, it can't come back down either because that air is coming up, as we just said. So some goes north and some goes south. If you look at what's going north, that arrow, that means that air's coming up in the northern portion of the Atlantic or over the southern United States, over places like maybe Mexico and then into Texas. Southern hemisphere, it's doing the same thing, going in the opposite direction, heading south. But as it stays aloft, what happens as it continues on its journey from 10 degrees to 20 degrees to 30 degrees from the equator, it cools adiabatically. The adiabatic lapse rate is the rate at which air cools as it rises. That's why when you go and you see sometimes it's raining down in the valley, but it's snowing up on the mountain. It's a lot colder at high elevations than it is at low elevations. That's basic physics. It's called adiabatic cooling. So now, as the air gets away from the equator, it starts to get heavy and cold, and eventually it sinks. And it sinks at about the time it gets to 30 degrees away from the equator, nearly a third of the way to the pole. It's so heavy compared to the temperatures around it that it just sinks. Once it sinks, it goes down, it hits the surface of planet Earth. Well, it's got to go somewhere. So let's look at the northern cell. In the northern cell, once it gets to the surface, we're going to see in another graph that some of it goes back toward the equator. That's what this arrow shows. That's what we're going to focus on now. But as you probably guess, some of it goes the other way. But let's not talk about that one yet. Let's talk about the one that comes back toward the equator. As it comes back toward the equator, what happens? It warms and it rises, and this keeps going. This is a cycle that never stops. And that cell is called a Hadley cell. So there are two Hadley cells on planet Earth. One just north of the equator, one just south of the equator. They are Hadley cells. Hadley cell, it's extremely important to understand this. Rising air where the sun is shining at its highest, and that tends to bring about condensation when the air rises and you get rain. Then you get a movement of drier air that's cool that eventually plummets down to the earth. Okay, this is a Hadley cell of circulation. The Hadley cell, we can think of it as starting at the equator. So that's 0 degrees in the middle of our planet here. And the Hadley cell, if you look at way out to the right or left, those arrows showing rising air at the equator. And then remember, when it gets to the tropopause, some goes north and some goes south. They go as they cool, they finally get so heavy they fall. Now, remember, as I told you, when that air falls, some of it comes back to the equator. That will form the Hadley cell, but some of it doesn't go back toward the equator. It goes the other way, away from the equator. North in the northern hemisphere, south in the southern hemisphere. And then as that air along the surface warms, it rises also. And as it rises, it goes up to the tropopause, and then some comes back and others go toward the pole. The portion that comes back constitutes what's called a feral cell. The portion that goes toward the pole constitutes what's called the polar cell. So if you notice, we have 3 cells of circulation in each hemisphere: the Hadley cell, the feral cell, and the polar cell. Now, here's the deal. If you look at the graphs in the atmosphere, way out to the right and to the left and on top and below the planet, you'll see that those show the directions of wind as though the Earth is not rotating. But if you look on the surface of the planet, those red arrows, the Earth is rotating. So the Hadley cell circulation that's coming back toward the equator does not come straight back toward the equator, even though in our simple model it did. Well, we had to walk before we can run. So we walked, now we're going to run. Because the Earth is turning, Hadley cell circulation cannot bring that air straight back down from 30 degrees to the equator, or straight up from the Earth's rotating. And it causes those winds to be twisted. Those winds, you can see the arrows, the ones coming in the northern Hadley cell come out of the northeast. In other words, yes, they come back toward the equator, but they twist toward the west. The ones that below the equator twist toward the west also. So they're southeasterlies. Those 2 sets of winds are called the trade winds. Those are called the trade winds. So you've heard about the trade winds, most of you. I would say few of you knew what the trade winds are. But what the trade winds are, they're northeasterly winds in the tropics, in the northern tropics, northeasterly flow, and a southeasterly flow in the southern tropics. Those are the trade winds. And they got that name because they had a big impact back in the days when they were sailing to bring things to the Americas and they relied on the winds. It had a big influence on merchant ships. You know, if you were doing trading, if you were trading things, and they did between Europe and the Americas, and you relied on sail, on wind power to get around, you certainly had to know where those winds were coming from. And you had to utilize those to sail. So they're called the trade winds. If you look in the feral cell, we live in a feral cell, by the way. I hope that everybody recognized that by now. We live inside a feral cell. And this graph, I love this graph, the folks who did it, but they put the 30-degree latitude a little too high. We're not at 30. That 30 should be down little bit south of that. They just misdrew this. So imagine that 30 is down over Georgia and Texas. We are at 40 degrees. Columbus is right at 40 degrees. Columbus, Ohio is 40 degrees north latitude. So it's pretty much right in the middle of the ferrule cell. And as you can see, ferrule cell circulation, okay, we know on the surface is from south to north, right, in the northern hemisphere. Hadley cell circulation is from north to south in the northern hemisphere. Ferrule cell is from south to north. But the rotation of the Earth causes it to hook around to the west. And that's why when you look and you see the weather map in the United States and there's a gigantic front out in Iowa, Wisconsin, Arkansas, and they show it, it's coming our way. It's coming our way because it's being guided by those what are called prevailing westerlies. And then you got the polar cell up there. I'll tell you some stories about that one of these days, the polar cell, because I've been in that, believe it or not. Okay, so here we have a cross-sectional view. The Hadley cell, look down on the right at the equator, rising air at the equator. Why? Because the sun shines there more. Now, I just want to say these cells shift, as I think your imagination will let you know. By June, the Earth is situated in such a way that the sun is shining not directly over the equator at all. The sun is shining directly overhead of about 23 degrees north. So that Hadley cell is shifted to our left. The rising air is not over the equator in June, July, August. Okay, all these things, this is Earth's climate engine and weather engine, they're dynamic. But in any case, what I want to show you on this graph is where the Hadley cell, I told you before, where that wind comes down, where the air comes down from the tropopause and comes to the surface at the Hadley cell, some hits the Earth, well, it all hits the Earth. Some goes toward the equator, some goes away from the equator and joins the ferrule cell. So now you're seeing a cross section of that. Aloft, we have a section of air that gets squeezed. And the Earth is rotating, and so that air just zooms by, and that's the jet stream. That particular jet stream, as you see between the Hadley and the ferrule cell, is the subtropical jet. We live inside a ferrule cell. But like I said, in the summer, that Hadley cell moves up toward us, and we find ourselves inside the Hadley cell, which means the subtropical jet is to our north. That's when we get hot, humid weather. That's our summer. In the winter, the Hadley cell moves way down south. The ferrule cell moves to the right. And guess what? The polar cell, yes, it comes here, right? I told you I've been in a polar cell. So have you. Because in the wintertime, we get a big Arctic blast, they call it. It's the polar jet stream, which separates the ferrule and the polar cell. And there you have that. So the northern and the southern hemisphere each have two jet streams that flow from west to east. They flow from west to east, the subtropical and the polar jets, because of the rotation of the Earth. One separates the Hadley cell from the ferrule cell and is called the subtropical jet. The other is the polar jet, which separates the ferrule cell from the polar cell. Now, we've got something called the ITCZ, the Intertropical Convergence Zone. Very important. Remember what we saw where the two Hadley cells came together, where the sun is shining directly over with a lot of energy? We get rising air. All right. There's a giant ring of storms around the planet. Giant ring of storms around the planet. And it's called the Intertropical Convergence Zone. It's the place where two Hadley cells meet and where the northeasterly and easterly trade winds meet. Now it moves from north to south with the seasons, okay? So the ITCZ in August is pretty far north. And in the winter, it's down below the equator. In April and May, it's right around the equator. It's the source of many of the hurricanes and tropical storms we see. All right. You'll get to know where it's located if you fly to Brazil like I do, because about the time you hit the ITCZ, you can feel it. When you go in July, everybody's flown and the captain comes on and says, we need you to buckle your seatbelts and get back in your seat. We got some pretty rough weather ahead. I'm not saying that's always the ITCZ, because there can be other storms that we're going to get into, but the ITCZ is always loaded with storms. And if you go down in August, you'll hit it earlier. It's further north than if you go down in January. You may even get all the way to Brazil and not even hit it in January. It's so far south. And here's a satellite image. How do you like that? There's your ITCZ. And look at those storms coming off the coast of Africa. In August and September, when the ITCZ is further north than this looks like it could be this time of year. Okay, May. It's north of the equator. The sun is shining north of the equator and has been now for 2 months, but it's not as high as it's going to get. That's why we're not in the hurricane season yet. You wonder, why is hurricane season mainly in August and September? Well, because that's when the ITCZ is further north. And see those storms coming off Africa, we already know that they tend to go from east to west because of the trade winds. We talked about that, how the earth causes those to run like that. The ITCZ moves in that direction. But if you look at that, imagine going up a little bit from where it is right now, up a little bit northerly in Africa. Storms start in that and they come all the way across the Atlantic Ocean, and boom, they land right into the Caribbean islands and hit Florida and the Carolinas. And so that's the source of much of our tropical weather that can be extremely destructive. And so that's where I would like to stop today. Once you be, many of you probably will need to watch this again. And it's the blessing of having this online for you to see again, because I gave you a lot of information. But before I go in another installment back to how you can see already looking in the Pacific Ocean, there's a lot of storm activity just north of the equator. And that's the area of El Nino. I just also want to say that you can see how much more area there is in the Pacific than the Atlantic. So we really don't have an El Nino equivalent in the Atlantic. The El Nino is because of the gigantic size of the Pacific Ocean. So that's the area over to the left where El Nino occurs, ITCZ. Over to the right is where we get a lot of our hurricanes.
I know that the winds can really pick up during certain times of the year. Does that also include like tornadoes? Are tornadoes a part of the weather patterns that we're talking about with the ITCZ?
Any large, powerful, violent storm system spawn tornadoes. A tornado is a very small, it's not a macro event. We're on a macro level here. The ITCZ is a macro phenomenon. It encircles the whole planet. Even hurricanes are a macro phenomenon because you could see them. If a hurricane developed on here, you could easily see it on this. It's big enough. It's hundreds of miles across, and it looks like a big spiral. A tornado is not a macro phenomenon. It's a micro phenomenon. In other words, most tornadoes are just a few hundred yards across. Some are just a few 20 yards across. Some, a really large one, maybe a mile across. But all of those are micro. They're small. And if you look in those red portions of these cells on the ITCZ, for example, a violent, that shows violence. That shows the darker the red, the greater the disturbance. A tornado forms for very localized reasons, but it tends to form only in very violent storms. You're not going to get a tornado in one of those cool winter showers, if it warms up a little bit and it's not snowing, it's 38 degrees in January here and it's a soft rain. That's not a violent event. That will not spawn a tornado. But if we go back and look where we see violent things occurring, all right, like look in the Ferrel cell, you see there's a lot of violence there where the Ferrel cell meets the polar cell. You see that giant thundercloud goes all the way up to the tropopause. Something that violent or as violent as where the Hadley cells come together. Those can spawn tornadoes, but tornadoes are very localized, small scale events. They're not large scale events.
The North and the South poles have been shifting. And, you're talking about the rotation, the magnetic Earth and South are shifting. Perhaps in a future program, you can talk a little bit about what that means to the global warming, the climate change, things of that nature.
Absolutely. Well, first of all, the North Pole and the South Pole, basically, when you stop and think about it, the North Pole is 90 degrees north. So if you climb those latitude lines, and again, I apologize, that 30 degrees should be down a little bit south. But if you go all the way to 90 degrees north, that's the North Pole. 90 degrees south latitude is the South Pole. Those are the poles, but the magnetic poles are something different, and they're not located at the North Pole, and they shift around quite a bit. The North Pole, where it is and the tilt of the Earth we talked about before, shifts over thousands of years, and it's very important. The location of the North Pole, how the Earth is tilted, has a big impact on ice ages and whether or not we have ice ages. But that happens over thousands of years. The shift of the magnetic poles doesn't really influence our weather, but it can affect magnets and electromagnetic fields and things like that in broadcasting and things. And we certainly talk about each one of those poles in the future.
Hey, we're talking with Dr. Tom Blaine. He's an associate professor with the Ohio State University, and he's our host of Earth is Our Home. Looking forward to our next episode, and thank you.